Hi, I'm Mitrevski from Bonn University in Germany, and I would like to present our work titled Representation and Experience-Based Learning of Explainable Models for Robot Action Execution. This is joint work with my PhD advisors, Professor Plöger and Professor Lakemeyer. Our work is motivated by one very desirable property that robots should have during action execution, namely that of diagnosing execution failures when they occur. We are interested in diagnosis for two main reasons. Diagnosis is first of all a closely related concept to explainability. A robot that can explain its decisions will help robot designers and users understand the reasons for a failure. Automated diagnosis, on the other hand, may also be useful for guided learning, as a robot that can diagnose itself will know which parts of its behavior it needs to correct. Action explainability and self-diagnosis depend on the action representation framework, and it is this aspect that we look at in this paper. Our work is based on the concept of parametrized skills. A parametrized skill, as the name suggests, is a representation of actions that makes an action dependent on some parameters that can be varied. For example, an object pulling action can be parameterized by the pulling duration, the pulling direction, or the pulling force. Parametrized skills can be modeled in a way that makes them predictive or generative. Prediction and generation combined make parametrized skills also suitable for probabilistic planning, as one can generate parameters with a high probability of predicted execution success. Our claim here is that parametrized skills are also suitable for the two additional aspects that we mentioned before, namely action explainability and failure diagnosis, such that in this paper we address the problem of representing and learning experience-driven robot action models. In this work we present a representation of parametrized actions that makes use of the concept of execution models, which figured in our earlier work. We particularly represent a parameterized action by two segments, namely a relational model of conditions under which the action succeeds, and a continuous model that is predictive since it maps action parameters to predicted execution success, but also generative as it can be used for parameterizing the action so that high predicted execution success is guaranteed. We represent the relational model by a set of logical predicates and qualitative attributes, which are defined separately for each action, while the continuous model is represented by a Gaussian process, which can encode prediction uncertainties. We learn these models from direct robot experience that is labeled by a teacher. An example of an execution model for the case of grasping an object, here a yogurt cup, is shown on the slide. Based on experience, the robot might learn that to grasp the cup successfully, it should approach the object from the side and align the gripper with it in a predefined coordinate system, such that the object can only be grasped if it is not occluded by another object. This would thus be its relational model of success. The continuous mapping, on the other hand, might represent the predicted success for a given offset between the gripper and the object center. What we see here may be the predicted success for a given height, where lower heights are associated with a lower success probability due to being closer to the table and thus more likely to lead to an arm collision. A key aspect of our model is that it allows representing actions in different qualitative modes. In particular, we allow the relational model to be represented by multiple relational models, one for each qualitative mode. This can be used for modeling context-aware robot behaviors, which is very important for being able to avoid contextual failures. The continuous model is shared between different modes, on the other hand, which can be seen as a form of multitask learning. Another important aspect of the model is that we allow for actions to be either free or unconstrained and constrained. In the case of a constrained action, we include the constraints in the input to the continuous model and ensure that they are satisfied during sampling. To learn the relational model of an execution model, we employ a learning procedure that uses a set of successful action executions and selects as preconditions those relations whose values vary little between executions. The variation of the values of a relation is captured by the entropy for each predicate P, such that the predicate is taken to be a precondition if its entropy is lower than a predefined threshold. The predicate value that is taken as a precondition of the action is then the one that appears most often in the successful execution samples. It should be noted that if we have multiple qualitative modes, the relational learning procedure is repeated once for each mode. The second component of an action execution model is a continuous model that represents the predicted execution success for a given action parameterization. For this, we use a Gaussian process regression model, which maps action parameters and constraints to predicted success probabilities, such that we use a conventional squared exponential kernel as shown here on the slide. There are two main reasons why we use a Gaussian process regression model instead of a different function approximator. Due to its nature, the model associates predicted success values with prediction uncertainties, such that the estimates move smoothly around the function spectrum. In addition, this representation allows easily incorporating various success functions, even ones including preferences, although we simply use a sparse 0-1 reward in this paper. On this slide, we see two algorithms, one which summarizes the procedure of learning an execution model, and one for sampling parameters from a learned model. During learning, the robot samples random execution parameters, which are then evaluated by a teacher. Given a set of such parameters and labels, as well as potentially a set of qualitative attributes, we extract the success preconditions and learn the continuous Gaussian process model. For execution with a learned model, we sample parameters from the training set given the Gaussian process model. In case the action is constrained, we first find the training constraints that are closest to the current constraints. The k-nearest neighbors algorithm is used for this purpose. We then sample parameters from the training set and take the uncertainty of the prediction for sampling execution parameters around the training point. We also verify whether execution given the selected sample agrees with the learned preconditions and reject samples that do not. We considered two use cases to evaluate our model. The first use case is that of handle grasping. We model the grasping action through the relation between the robot's end effector P and the bounding box B of the handle to be grasped, such that we use the relations shown on the slide for representing the relational model. We parameterize this action by the offset of the end effector to the center of the handle's bounding box, such that we determine the bounding box using a standard object detector trained on our custom handle dataset. Our second use case considers a constrained action, namely pulling an object to a desired goal region. For simplicity, the robot only pulls the object towards itself with a constant speed, so the action is only parameterized by the pulling duration and not the pulling direction. The relational model encodes the relation between the object and the target pose. We model this action in two qualitative modes based on the distance of the object to the robot, which we simply represent as short and long. The pulling duration is represented qualitatively as well, also as short and long. In the experimental analysis, we wanted to answer two questions, namely whether the representation can improve the execution of our HSR robot, and also whether the learned model is helpful to the continuous model while generating samples. We performed the handle grasping action for two handles, a drawer and a fridge, and the pulling action was performed with a single object, a noodle cup. In all experiments, we collected 50 labeled samples and then repeated the execution for 50 times with the learned models. On this slide, we can see the relational models that the robot learned for grasping handles. We can see that the representation includes that the robot's end effector has to be in front of the handle while grasping and also centered along one of the dimensions, depending on the handle. The representation also includes predicates that should not hold for successful execution, such as that the end effector should not be above or below the handle. The relational model for the object pulling action encodes the fact that the object should be centered with the goal region. As a reminder, this is because our simplified action model only considers pulling an object towards the robot. In the case of a long distance, the object should also be behind the region. This is not necessarily a precondition in the short distance case, as the scenario in which the object already starts at the goal region is included here. The pulling duration changes depending on the qualitative distance as well. In this particular case, we can say that the robot has qualitatively learned that for a constant pulling speed, distance and time are proportional to each other. For the quantitative analysis, we compare two different versions of our sampling procedure, namely one in which we accept all generated execution samples from the model, which we refer to as R-opt, and the sampling algorithm shown before, in which we only accept samples that agree with the learned preconditions. We refer to this sampling procedure as R+opt. As shown in the tables, both variants of the learned model improve the execution success, but the one in which the preconditions are verified during sampling leads to higher success in general. Here we see our HSR robot, first during the learning data collection process, and then when using the learned models for executing the actions. This is one typical failure in which the robot fails to grasp the handle due to a slightly incorrect estimate of the handle's position. Another typical failure is that the robot goes a bit too far, hits the drawer, and then doesn't grasp the handle. This is now execution with parameters sampled from the learned model, where we see that the robot has improved its performance in the grasping action. Due to it being better at grasping, the robot has also improved at opening the drawer, even though the data labels only capture the success of handle grasps. The observations are similar for the pulling action. During data collection, the object is usually either not pulled far enough or is pulled too far, as we can see here. After learning, the object is pulled successfully more often and in both qualitative modes, namely when the object is a bit further from the robot and when it is closer to it. From the experiments, we can conclude that our model improves the execution success of the robot and that the relational and continuous models working together are better at constraining the execution parameters than the continuous model alone. Additionally, an interesting observation from the experiments is that the learned models almost eliminated severe execution failures, and most failures were due to the robot being too conservative in a sense. Our implementation of the execution models of the handle grasping and object pulling actions, as well as guidelines for reproducing our experiments, can be found in our GitHub repository given here on the slide. There are various aspects that future work needs to improve. First of all, fault models could be learned in addition to the success models, and the same relations could be used for this purpose. The learned model could also be used for diagnosing faults through alternative action parametrizations. Additionally, the learned models could be generalized to different objects and scenarios using an object ontology or a scene ontology respectively. A simulation could also be used for more extensive experience acquisition. The representation could be combined with an action projection framework. This would be in the context of complete tasks. And the learned models could potentially be used to constrain the experience acquisition during reinforcement learning, thereby contributing to a safer learning process. Thank you.